And today is the start of this room's sessions, and it is digging for IE11 Sandbox escapes. And your speaker today is James Forshaw.
Hi, yes, good morning. It's impressive to see so many people at this ungodly hour. So I'm here to speak about some of the stuff I've done in IE, specifically IE11, to find ways out of its sandbox, specifically on Windows 8, which has a new enhanced sandbox, which is better than the old one, apparently. Some would beg to differ. So it is in a workshop format. I've presented this before at a few different conferences, where it was more specifically about the bugs I found during the Microsoft bug bounty period, which was running last year, just prior to Black Hat. But I hope to now do sort of a more expanded talk about my sort of methodology of how I go about finding sandbox escapes in IE, what sort of techniques I use. It will still go into some of the bugs, because the bugs are quite useful to sort of demonstrate what types of things you can actually find, how you can actually exploit those sort of scenarios you find yourself in. And as this is a workshop, this isn't just a straight presentation to people. If people have questions, if I don't make the blindest bit of sense during the workshop, I encourage people to ask questions, bug me about stuff. I hopefully should answer at least most sort of questions about this, but if not, then I'm sure I can bluff my way through and make it up as I go along. So people don't have to obviously actually participate. I see some people with laptops here, but if you want to, you can. I've got some links, as you can see right at the bottom of the slides. There's a link to my GitHub page where you can actually download pre-built binaries for some of the example exploits and some of the tools I'm going to use. And there's also some other resources, sort of specifically, there's actually the source code there as well on my GitHub page, so if you actually want to look at it in more detail, you can do so. But you don't have, as I say, you don't have to. You can just listen to me waffle on for 2 hours if you like. Now I'm going to go into some detail of the IE sandbox, but I'm not going to go into sort of intricate minutiae about it. So there's actually a sort of quite good write-up by Mark Yason, who works for IBM X-Force, who presented it a few times and goes into far more depth about the IE sandbox implementation. So it's definitely recommended you go and try and pick that up, and if you want to actually read into more about the sandbox stuff. So this is my background. I do have to give some sort of background, otherwise we've got no sort of nice base with which to play. And IE is fairly typical. It's one of the first browser sandboxes, if not the first browser sandbox to come along. Originally developed in Vista, and so under something called protected mode. And what it used was, it used a new feature of Vista called integrity levels, or mandatory integrity levels, which allows you to restrict what a process can do without necessarily being a different user. And so what the actual sort of basic setup is you've got a low permission zone, which is running with less permissions, and this is where all your internet content is rendered. So whenever you browse to a website, it will be rendered, the HTML will be parsed, the JavaScript will be run within this lower privileged code. So the theory being, this untrusted data which is getting stuck into Internet Explorer, if there is a remote code execution vulnerability, and let's face it, IE has 1 or 2 remote code execution vulnerabilities, the worst that can happen is you get contained within this sandbox, and that's the idea. Now, you wouldn't be able to do a lot, you wouldn't be able to do very much if that was the only piece of code running. So there's actually a normal privileged piece of code, the sort of frame process, which is actually the thing which sort of renders the window. And this contains the functionality to sort of support these low privileged tabs, low privileged sandbox applications. And it does that through a broker. So there's a piece of code in this higher privileged process which sort of brokers functions. So if you want to open a file, for example, you talk to the broker and say, hey, I want to open this file, will you let me do it? and the broker is then responsible for the sort of security enforcement of that. Now, in contrast to Chrome Sandbox, for example, or the Safari Sandbox, IE has a really weird sort of view on trust. So Internet Zone trusts, or the internet-facing components, are absolutely untrusted and run with its low privilege. However, if you browse to an intranet site, this is usually categorized by a host name with no dots in it, or something which is explicitly marked as in the Internet Zone. It actually runs it at the normal user permissions. So if you're able to run an exploit within that an intranet zone page, you don't actually even have to deal with the sandbox. And as ZDI demonstrated the other week, that you can use this to abuse IE to actually break out of the sandbox directly. And this is something Microsoft apparently can't be bothered to fix. So that's pretty sad. Yeah, everything should run in the sandbox process. Nothing should be run outside of that, from internet control. So one of the limitations on the original implementation, protected mode, was all this low integrity level did was it restricted the ability to write to resources. So the usual modus operandi sort of a remote code execution vulnerability would be you pop IE, you run code, and then you can install your malware permanently, and it just runs forever. You put it, say, in the startup folder or somewhere like that, or in the registry, or some other cunning way. The idea here is you can't easily do that with the sandbox, because you can't write to those locations on disk. But there's nothing stopping a piece of malware sitting there temporarily, hoovering off your data, because you can read everything. It doesn't matter. So with Windows 8, they added a new sandboxing technology, app containers. It's what actually underpins the sort of metro applications, or modern applications, or whatever the hell they're calling them this week. And they use this now as the new enhanced protected mode sandbox, which is a lot more restrictive. Specifically, you need to actually give explicit permissions to both read and write to resources. And this is done through the usual access control mechanisms in Windows. So, for example, IE has a special SID associated with the process, and so you can add this special SID into an access control list and give out access to IE only. There's also a group SID, the All Applications Packages group SID, which allows you to access resources based on groups. And then EPM goes even further. So app containers allow you to do interesting sandboxing techniques. So it has something called capabilities, and these reflect what your application is allowed to do. So there's things like, can I access the internet at all? And that's a capability. If you have no capability, if the capability flag is not set for internet access, you can't get internet access, and that's the end of it. There's a few others. Another interesting one is hosting local servers, and the ZDI Sandbox Escape demonstrated a couple of months ago, is actually will not directly work in EPM because you can't bind the local web server and use that to do a loopback attack and get internet permissions. So it further sort of reduces the attack surface from the perspective of the operating system. But of course, as I say, it actually has to do something useful, so it has the broker associated with it, which is implemented over COM. So COM is a technology which has been around for many, many years in Windows, and it can be used to do a sort of out-of-process access to resources. So let's just at least have a quick look at IE. Yeah, well, bit of advertising from my friends there, obviously. Right, so we can actually just look at, if I bring up a copy of IE. So the desktop IE is designed for sort of legacy use, they say, because on Windows 8, obviously, there's the full screen version of IE. But the full screen version of IE is always running with the enhanced protected mode on. There's no way of turning that off, whereas the desktop mode as we'll see, isn't always a guarantee. So we can actually just look in, if you bring up like Process Explorer, and we can zoom in a bit. So we've got a copy of IE here. This is actually the metroized IE. As you see, it's because it's suspended. And we can see that we've got a medium process, which is our broker process, is our frame process doing the rendering. And then we've got our sandboxed application, our app container. And we can see if we scroll further down, we should also see a copy of desktop IE, which has the same medium and app container. But actually, security-wise, in contrast to something like the Chrome Sandbox, which is actually really, really restrictive of what it allows you to do, you can see the actual permissions given to the low-integrity Sandbox is actually quite a lot. Theoretically, you can shut down the machine and change the time zone and do other weird stuff, potentially. Whereas if you look at sort of Chrome, it gives you nothing and really, really heavily restricts what you're allowed to do. So even before we've even started, there's a certain amount of sort of leeway in actually the way in which IE is sandboxing itself. And this is for legacy reasons. So IE has a lot of enterprise users. It has a lot of unfortunate legacy it needs to carry along with it. It needs to make sure that as few applications break as possible. And so unfortunately, the security is less because it has to support those scenarios, which is unfortunate. So let's go back to the presentation. So one of the things which comes about through this legacy support is the fact that there's loads of like old plugins, load of old ActiveX controls, toolbars, all that sort of useless junk which IE generally accumulates. But Microsoft didn't want IE to just drop support for those features. So it tried to emulate a sort of environment in which the control would normally find itself to try and make it at least amenable to it. So for example, the old control with IE6 would be running its normal permissions, and it might want to create a new process which does something. And unfortunately, that shouldn't be allowed, or at least if it is allowed, would run with its lower permission. And that may then break, and then it wouldn't work. So what it does is it proxies along certain function calls. So create process, or the co-create instance, which is used for COM instantiation. It will actually proxy these through the broker itself. So the broker exposes functions which implement these at the user level. So in theory, a poorly written extension can still use create process, and the worst that will happen is the user has to click a box saying, yes, I allow you to run command.exe or whatever. And it does this security decision through an elevation policy. So the elevation policy is something written into registry and contains basically the information about what processes are allowed to run, what COM objects are allowed to instantiate. And I'll show that in a bit more detail later as we go into sort of my methodology of finding bugs. But basically, you can just see this in the registry, and it's effectively documented. Now, there's a few different policies to support different scenarios. The one you're probably most interested in is the ones which basically say, run this executable completely silently with arbitrary command line, do whatever you want. And those are the ones you really want to sort of look for when you're going actually after finding bugs in the elevation policy. But there's other ones. There's one which actually explicitly states sort of, this process is never allowed to launch. You can't even prompt for it. So command.exe, for example, is set as, do not ever give the user the ability to completely screw themselves over. But of course, things like WScript, which runs arbitrary JavaScript or anything else like that, oh, that's fine. You can at least just prompt for that, it'll be fine. So it's a bit sort of, it's a bit pointless, but yeah, well. Now, IE is it's not a monolithic application. There's a lot of component parts, and we need to kind of know which parts of the Internet Explorer are actually important for Sandbox. And it turns out that IExplorer.exe, the thing you actually run, is little more than a shim around the IE frame DLL. And this is actually where a lot of the real guts of IE actually sit. So when you're going to do reverse engineering of IE, going to IExplorer.exe is going to get you pretty much nowhere. So you have to go for IE frame. And then there's also other support routines. There's IE for doing remoting and proxying of function calls, which are also generally somewhat important, but perhaps less so. Now, if you know much about IE, you'll notice that things like MS-HTML, which is the HTML rendered Trident engine, that's got absolutely nothing to do with the sandbox, realistically. It has no real concept of the sandboxing mechanism, or at least to a certain degree. I'm sure it does have some knowledge of it. But if you're actually looking for sandbox escapes, MS-HTML is completely useless and is unlikely to be something you want to go look for. Okay. So given all that information, there's some sort of level of attack surface you can kind of infer from the way in which IE does its sandboxing. And this is probably fairly similar to pretty much any other sandboxed application out there. So you've got things like accessible resources. So you've got this code running at low. What actual resources, what files, what registry keys, what processes can those resources access, or can those processes access directly without ever invoking any of the other sandboxing mechanisms? So if you can find something which you can access, there might be a way of exploiting that. You've then got the IPC boundary itself. So there's a bit of inter-process communication. Obviously, the internet process has to talk to the broker in some fashion. In this case, it's DCOM. There's probably stuff in the boundary layers which have interesting problems. That's certainly true. There's the broker itself. The broker is obviously exposing functions which should be secure, but may not be. And I think it should demonstrate that that's definitely the case. And finally, the other major attack surface is what is actually allowed through this elevation policy. What processes can you run? What objects can you access? If any of them do anything bad, you potentially got a sandbox escape right there. Okay. So that's my basic background. Has anyone got any questions about the sort of IE sandbox stuff? There's not much. Yeah.
Windows 7, the advanced selection of also familiar using the applicator? Or using Windows 8?
Okay, so Windows 7 can only run protected mode. It's Windows 8 specific is enhanced protected mode because it requires the app container mechanism to work.
The security option from IE11 and Windows 7 enhanced protected mode, I'm not sure what it does. Is it also app container thing?
I think it does some extra features, things like 64-bit processors, but I think it can't use the app container mechanism. I think it doesn't actually provide you much extra on top of what you'd normally get in protected mode. Yeah, the question was, on Windows 7, you can set a flag saying turn on enhanced protected mode. The question was, does that use some sort of app container mechanism like on Windows 8? And the basic answer is Windows 7 does not have the app container mechanism, so any of the more in Windows 8 specific features like capabilities and the restricted write access are not something you can get through on Windows 7. That makes sense? Okay. Okay. Now, of course, I think Microsoft officially state that protected mode, so the Windows, like prior to Windows 8, the normal protected mode is not a security boundary. The usual sort of get out clause for Microsoft to say, we don't want to fix any bugs in this particular area. So it turns out that you actually have to sort of enable enhanced protected mode. You have to sort of turn it on above and beyond normal protected mode. Yes, yes. You can have both on Windows 8 if you choose. Now, it was defaulting. The first version of RTM 8.1 of Windows 8 using IE11, it defaulted to enhanced protected mode being on. And that was deemed quite a good thing because much as it may be not the greatest, Sandbox is at least better than protected mode. But presumably for compatibility reasons, in one of the subsequent IE 11 security updates, that was actually now disabled by default automatically. So you actually have to go and turn it on, unfortunately. So if we actually want to test this, we kind of need to actually turn it on before you can actually do any testing of EPM, because the only bugs Microsoft theoretically will fix is the ones you will find in enhanced protected mode. We actually see in IE itself, when we're actually doing tests, you want to make sure that you're actually getting a sandbox at all, because there's various places where you can accidentally turn off the sandbox. So if you right-click a page in IE, you can actually see, as I show here, you can actually see what sandbox mode is running. And if you're just normal protected mode, it will just say on. And if you're enhanced, it will say enhanced. If you're running with no sandbox at all, it will say off. So yeah, that's just a bit of, and yeah, the trick is when you're doing this testing not to accidentally end up in no sandbox or protected mode, especially if you're actually trying to do it through a remote code execution, because there's various places where you could accidentally turn off the sandbox, such as intranet zones or local files. So you've got to make sure you don't do that. Now, when I did this initial research, and arguably the research I'm doing now, I didn't actually have a remote code execution in IE. So how am I actually going to test a sandbox escape when I can't get code to run in the process? Well, obviously with Windows, it gives you plenty of opportunity to inject your code into other processes. And so if you've not seen a simple DLL injector using create remote thread, I'd be surprised. So that's basically all you have to do. You can just inject an arbitrary DLL into the sandbox process, run your test, run your escape, see if it works. The only proviso is you need to be able to give IE access to that DLL. Obviously, if you say load this DLL and you've not given read permissions to it, it's not going to get very far. So the simplest way, change the access control list, add the all application packages group SID, the group to it. You can then get read access to that file and you can inject. So you can build up a simple test harness. There's example code for this on my GitHub page. So we can just do a little simple test just to make sure it's all working. So I do have, okay. So I have an example one here. So hopefully, I don't know whether we can see that. Is that right? Okay. So the example code which I've got has an inject DLL program which will just allow you to find, inject an arbitrary DLL into the process. And it has a -L switch just to print out the current instances of IE running. And we obviously want to target the low privilege one. This is the sandboxed one. So we'll just inject DLL into 2580 and example DLL. And this doesn't actually do any sandbox escapes, but it will just demonstrate that things are actually working. We can see in the debugger, example.dll ran, and hopefully somewhere, there it is. So it just pops up a message box. And this is actually running, it's running in the low privilege process. So this is directly running as a low privilege. So hopefully the example code should give you a reasonable way of actually writing your own stuff. It's just a simple framework. You can just write your own attempt at a sandbox escape, run it in this, and you can actually just get code to run.
So that injected into the sandbox, right?
Yes, so the inject DLL program creates uses a technique to inject a dynamic library into the sandboxed process. It will then run in the sandbox process, and you can obviously then do a test for the actual security of that. Okay. Now, when I actually came to doing a lot of the sandbox work, you will find that a lot of the interfaces into IE sandbox are all running COM. So the big challenge usually is to actually you've got to kind of reverse engineer COM. Obviously, there's very little open source for anything to do with Internet Explorer. So you need to have a bit of sort of knowledge of what to look for in COM itself. And I unfortunately can't talk about COM without at least a little bit of background in how COM is structured. So there's sort of three main concepts in the way COM works. And it's used for, the acronym is basically Common Object Model. It's designed for sort of sharing objects without worrying about like binary compatibility, which is something C++ has traditionally not done very well. So at the top, you have what is called a server. And a server could be an executable, could be a DLL. And this is the block of code which implements your COM objects. And that server is registered in the registry and says, I support this COM object. And that server can have more than one COM object, for example, so it can have multiple different classes. And these are the classes which are referred to using special unique identifiers. And then finally, each class itself can support multiple ways of looking at it with different functions, and these are called interfaces. And there's sort of predetermined ways of going through each step. So for example, if you call the function co-create instance in your code, you'll instantiate a class which is from the server, and then that class has a function called query interface, which effectively allows you to cast between different interfaces. And that will become very important later on when you're trying to find for, the attack surface of a COM object or broker object which is exposed to you in the sandbox. And everything's using these unique identifiers. You'll see them everywhere. It's used in Explorer and all that sort of stuff. So it's all fair. You can find documentation about this. It's not too bad. Now, when we want to actually access we want to break out, we want to get our first COM object, we kind of have to try and talk to this broker. And I've said the broker is implemented using COM, and that's obviously quite important. So this is just a little bit of code which gets the broker for you. So when IE starts up, the main process creates this broker object and then effectively hands it off to each sandbox process and says, here, if you need to talk back to me, talk via this COM object. And it's not documented, of course, because it's all internal to IE, but it's fairly easy to reverse engineer it and find out how to do it. So that's your object. Now then, the object has potentially multiple interfaces, multiple ways of looking at that object. And the main one for the broker is this IE user broker. And you can actually see most of the functions on there are actually related to that hooking I was talking about. So for example, create process. When you call create process in a sandbox, there's a little shim which redirects you to the broker. And the broker then exposes a function which then does all the security checks and all that sort of stuff. But how do you actually get that out? How do you actually find out what those functions are called? Well, obviously it turns out Microsoft is very generous in this regard and gives everyone public symbols to IE. And we can go and pull those out using, if you've got a copy of IDA, you can pull them out fairly easily using a simple script. So I'll hopefully have IE frame. So I've loaded IE frame into IDA and pulled in its PDB file, so that it's public symbol file. And we can sort of track down, hopefully if it works. Okay. So we can easily track down the broker functions. They're all fairly obviously named. C, IE user broker object. And if we actually go to one of these, it'll obviously give you all the usual stuff IDA does. We want to try and get it into a form we can call. So you can just take these manually and just type them in manually. As I go along, I'll show you some interfaces which have slightly more than 6 functions on. So at that point, you'll be there forever if you try and type them all in. So we can actually go and see. We actually pick one which is exposed. We can go to its reference. If we go to its reference, we find the vtable of that object. So COM is all implemented using virtual tables, which is sort of an idiom from C++. And effectively, this is a list of function pointers to all the functions in that interface. And I've got some scripts which I should have on the desktop. Where Where is it? Obviously, I don't have it on the desktop. Right. And I've just got a script which, again, is available online. And it's a simple IDA Python script which will go through and, for a certain selection, try and generate you a simple C++ interface file that you can then recall and actually do direct work with. So let's try and run that. Okay. So first, I select just out the list of functions I want to expose, then run script file, and vtable to definition. I run that, and hopefully, if I can get it to expose here. So just in my output window, I've now got a C++ structure, and usually either the public symbols, because most of this is written in C++, there's mangled symbols in the public symbols, and usually this allows you to extract a reasonable amount of type information about the function call parameters. If not, usually IDA is clever enough to try and work out some of them already for you. So the actual output, for the most part, will be reasonably typed up, so you can just plug it straight into your code and call functions directly on it. Now, it doesn't tell you what those parameters do, and that's, of course, the challenge of reverse engineering, to work out what the hell they actually do. But that's for later. Okay. Now, when it comes to COM, there's two ways of running COM. You can either run it in process, which obviously in this case would just be running it in this Sandbox instance. So that doesn't actually provide you with much in the way of useful information. Most of the stuff is running out of process, and especially for third-party code, for example, things like Flash has a broker to allow you to access certain things in IE. You've got to actually track down in the reverse engineering where that function is. This is particularly important if you have no symbols. So Adobe obviously don't provide symbols for the IE Flash broker. So you've got to kind of use IDA to actually track this down. And so the best way to do this is there is a specific sort of calling convention used in registration of out-of-process COM, and it's using this co-register class object function. And through that, we can kind of trace through, work out where the actual class is, which is implementing these functions, and we can then extract and reverse engineer those functions itself. Now, sometimes you get lucky, and there's also type libraries. So COM has the facility to have a self-describing sort of metadata file associated with it, and this gives you pretty much all the sort of function information for the exposed interfaces. And if you're lucky, and in this case Flash Broker, you are very lucky, you actually get a full type library which tells you exactly how to call all the functions, and usually what even the parameters are. It doesn't necessarily give you a full tutorial of what you need to do to get it to run, but it's certainly better than nothing. So I'll quickly just go through sort of tracking down Flash Broker's stuff. So this is default install of Windows 8. Because Windows 8, or Windows 8 and Windows 8.1 come with Flash built in order to support it running in Metro mode, this is actually built in to all versions of Windows 8. And I actually found some Sandbox escapes in Flash Broker, which at least try and look at one later on. But yeah, we want to actually try and dig through and try and find our functions. And obviously I've somewhat annotated it already. So we have a co-register class object, which you can obviously browse through to where it gets called. And so this is where it's registering what is called the class factory. So you don't register the COM object directly, you register a factory object, which when you call it, will instantiate a new COM object. So we can tell from our function parameters where our class factory is, and we can obviously, which is ESI, and then we can dig out, okay, the constructor's here, because it has to instantiate a copy of this class factory. We can then go through that one, and then we can go through that one, and obviously, like a little rabbit warren, you could be there all day, but eventually, you should find the actual vtable itself. And again, from there, you can do breakpointing, or you can kind of tie it up to that type library, because that type library gives you all that useful information in there to actually process and work out what you need to call. Because obviously you want to reverse engineer the functions because you want to find vulnerabilities in them. You could just try and just call the functions, but it sometimes is easier, sit there with the disassembly, maybe, and actually work out what those functions are doing. Okay. So that was a bit of a long background of the sort of my reverse engineering methodology, the sort of things you need to kind of know to actually go out and try and find IE sandbox escapes, the sort of comm stuff and how the sandbox works. So now actually let's go into trying to find some vulnerabilities. And the first, the sort of simplest one to go looking for, in my opinion, is the access to accessible resources. So accessible resources are isolated from the outside. So effectively, if you know what permissions that sandbox process runs with, you can easily offline, by just trawling the file system or trawling the registry, find resources you can directly access and directly write to. And there's various tools to do this. I didn't find one which kind of worked in the right way for narrowing down functions, so I just wrote some PowerShell scripts. And PowerShell is usually gives you pretty much full access to like ACLs and security aspects, so you can just write a real simple and dirty script. In this case, this is for trawling registry information. And when we're dealing with the enhanced protected mode sandbox, you need to know either can the IE process SID access it, or can the group SID access it? And so you're basically looking for anything which can write using one of these two SIDs. So again, we can just sort of quickly run that. If I bring up PowerShell. Okay. Scripts. So I've got a couple of PowerShell scripts in here. Find accessible files and find accessible keys. So effectively that's just the same as I had before. And if I just run that, obviously ignore the various errors, because obviously I'm running as a normal user, so some things you can't directly access. And hopefully, if it all goes to plan. Okay. So now it starts spitting out all these keys. And so these are our registry keys you can directly access in from the IE sandbox process. So if I just run regedit, oops, we can go and pick one of these. So software, Microsoft Internet Explorer, either software, Microsoft Internet Explorer, low registry. So these are all stuff you can access directly. And then we can see that this is the IE user, the 4096. You can always remember that, it's quite easy. And it has full control. So anyone can, from a sandbox process, can modify, write, manipulate that registry key. Now, it's all very well finding these resources, but what can you actually do with them once you've found them? Well, there's usually two ways of exploiting accessible resources. Either through stupidity or whatever, that resource has direct security implications. So that resource has some security critical function, such as, is the sandbox on or off? And if you find something like that, you can potentially just modify the resource to turn off the sandbox. The second sort of main way of exploiting accessible resources is trying to exploit the relationship between sort of a higher privilege process and a lower privilege process. So as a good example, if the medium level, the user level version of IE writes to a file, which you can also manipulate at low privilege, potentially there's a way of exploiting that to either gain arbitrary resource modification or accessing other files you shouldn't be allowed to do. So in the general case, number one is rare, fairly rare in terms of finding those sort of things. It does happen, but it's less significant. But number two is definitely sort of something you can find, as I'll just demonstrate. So I usually then try and find out who's calling it, because the best way to find a vulnerability in the stuff, in my opinion, is to find out who is responsible for manipulating that resource, and then obviously once you've found that particular function, you can then dig in straight in and actually look at it, and reverse engineer it, and work out what you're doing. And I find the best tool for that, for resource access, is Process Monitor. And hopefully someone in this audience has at least used Process Monitor once. Whether you've used it to try and dig out where a vulnerable piece of code is sitting, I don't know. But yeah, you can set symbols up in Process Monitor to effectively access, find out in sort of Microsoft code at least, using public symbols, exactly where in the code you need to go looking for to work out who's accessing that resource. So I should have just a very quick demo of, sorry about this. Restore that. So yeah, it's usually, this is always my go-to. If I need to see if something's accessing that resource, who's doing it, straight to Process Monitor. If you can't see in Process Monitor, then life gets considerably more difficult, but it's hopefully not too bad. So if we run a new copy of IE up, we can see it obviously accessing an awful lot of crap. Low registry. So this is what we were looking at before. Oops. And so we can see, say, low registry him. Let's just zoom back out, otherwise we'll not see anything. And then you can just look at the stack frame, and we can see that there's like a set protecting my reg key only function. And maybe that has a vulnerability, who knows? So I obviously went a bit into detail of that and did some reverse engineering. And it turned out that this function was just this relatively simple flow. So it tries to create this registry key, which we've identified. If that key doesn't exist, it'll create it. And this is running at the medium level process. This is not running in the Sandbox process. If it doesn't exist, it'll create it. It then tries to check whether the low privilege process can access that registry key. Can it read and write to that key? If not, it will actually modify it so that the access control list says, yes, you can access that registry key. And that to me just looked like a potentially dangerous function. Because we can, in theory, induce the user level version of IE to create this registry key, but we can modify it from the Sandbox process. So can we exploit that? Well, clearly we can, otherwise I wouldn't talk about it. And this comes down to one of the techniques of attacking registry access in the low privilege process. And it's something called registry symbolic links, and I don't know whether, I'm sure anyone who's used a single Unix system will know what a symbolic link is, but probably not many people realize that the Windows registry has symbolic link functionality in it. That's because Microsoft are somewhat loath to document this. If you go to MSDN, there's generally oblique references to this functionality. So key create link, reserved for system use. Okay, cool, thanks. Fortunately, other people have done the digging and worked out how to use this. But what a symbolic link gives you is it allows you to write something into the registry which points to a completely different part of the registry. And hopefully, that should be relatively obvious how you would exploit this, because you can modify the registry so that you've got a symbolic link, and when the medium level process goes to write it, it will actually write somewhere completely different. And now you can write into some sort of security critical area of the registry. And I chose, actually for my exploit purposes, I chose the elevation policy. And it turns out the elevation policy has both a system level and a user level component, and we can write to the user level one quite easily. And from that, we can add our own processes to the elevation policy and jump, like pop calc quite easily out of Sandbox. So it's a fairly simple attack once you actually get down to it. You can create a symbolic link. As I say, you can find code for it online. The example code I provide on my GitHub page also has example code for it. And you use that, I chose a particular registry key and spun up a copy of IE. And once IE runs, the registry key gets created. But it doesn't create the right registry key. It creates the registry key I pointed it at. And crucially, it also sets the security of that registry key to allow me access from the Sandbox process. So at the very least, this is an arbitrary registry key creation, which may or may not be that useful. But because it sets the security, I can now modify that at will. I can fill in my registry elevation policy, do a bit of refreshing, and obviously you can get calc to pop up quite easily.
So that bypasses any permissions on the registry.
Yes, so yeah, trying to think of the best way to put it. Yeah, the question was, can you, does this bypass the protection on the registry area? And yes, it basically circumvents it allows me to create a accessible part of the registry on my own control in some other part of the protected registry, and so bypass the security restrictions on the registry. So obviously I can quickly demo that. Unfortunately, I've kind of got to stop that. Close. Yeah, fair enough. The wonderful world of snapshots and VMs. It's how do you do vulnerability research before VMs and snapshots? I don't know. Okay. So it turns out that Microsoft fixed this bug twice. They actually half-fixed it first, and so they fixed the part where it was checking for the registry key to see whether it existed, and they modified it so instead of creating the registry key directly, it would open the symbolic link. So if it opened the symbolic link, it would realize that, oh, there's already something sitting here, like waiting to do me over, so I'm not going to continue. But it turns out, if you could bypass that open check, the create check didn't check for the symbolic link, and so you could still exploit it through various different means. So they actually had to fix it again in a later security fix, which is always amusing. So let's see if I can remember which one this is. Not that one. I'm sure actually I wrote it down on the slides, didn't I? Yeah. Sorry, I'm obviously. Okay, so all my escapes have got like debugging information, and kind of gives you a rough idea of where it's currently sitting. And we've got a copy of IE running, so we can obviously do inject DLL list 2058. Okay, so 2580 CVE and this one, and if I just breakpoint on this, the CVE 2013, 50, 45. Okay, so hopefully, yeah. So obviously you can now obviously step through everything, and so this function was creating our arbitrary registry keys, and we can actually see, you could run up process monitor, for example, and actually see which piece of code is doing this each time. And eventually we get through to the end, and obviously count pops up, and this is obviously now running as the medium integrity and has bypassed the Sandbox. And this was from EPM originally into that. Okay. So it's not just files which we're dealing with, not just registry keys we're dealing with. Obviously, files as well are also potentially of interest. And I suppose the thing here is, can we do something similar with files as we can with registry keys? Well, it turns out, sort of. Now, Vista introduced the concept of a file symbolic link to Windows. Prior to that, it had no ability to do file-level symbolic links. But unfortunately, either for security reasons or just for reliability reasons, Microsoft made it so that you required a specific permission to create these symbolic links. And the only people by default who have this permission are administrators. And if you're an administrator, well, I don't think it matters anymore. So there's obviously a problem there. But it turns out that if you're only worrying about directories, NT's had symbolic links for quite a long time, since at least Windows 2000. And these are actually usually called junctions, and they're used at a directory level. So you can't redirect a single file access, but potentially if you can create a directory, you can repurpose it and use that as a symbolic link into somewhere else. So if you can access a resource, a file resource, and then get a higher privileged process to write to that resource, you potentially can get a write to an arbitrary location. And this actually requires, fortunately, no privileges above and beyond the ability to create an arbitrary directory. So as long as you can get write access to any directory on the file system, you can modify it, in theory, to be a junction. So this is where one of my Flash Broker bugs came in. Flash Broker actually implements a file API because it wants to write things like your shared objects files into the protected parts of the file system. So it has functions like broker create file and broker create directory. But obviously, if it just wrote to anywhere, there's a clear security issue there. So it has to do something different. And what it does is it limits the locations you can write to specific areas of the file system. So I've shown them in the little table below. You've got things like the roaming Adobe Flash Player. This is where the sort of shared objects live. There's also a Macromedia one, because obviously Flash was written originally by Macromedia, who were bought out by Adobe. So that name sort of sits there for legacy reasons. But one interesting place they do allow you to write to is the temp directory. And the temp directory theoretically is under control of the low privilege process, because the low privilege process still needs to write temporary files somewhere. And in this case, potentially, if you can write to that, you can create a junction and then write your arbitrary file through the Flash Broker API. So yeah, unfortunately, this only works in protected mode. But Adobe still fixed it because they weren't Microsoft. But this is because in enhanced protected mode, it redirects the temp directory. So it redirects it to a completely different location, to your normal user's directory. But if we at least assume that we can use protected mode, well, it's actually fairly simple to exploit. So you create a directory under the temp folder, call it whatever you want, and then use the APIs, write that directory, write that file, and you can write it to anywhere you like. So I think this would probably be the last demo of this session, because we've got 5 minutes left, so I think it kind of works out quite well. Okay. And back to pissing around with this. So, turn off. So I've got a VM which has EPM turned off. So this is just running traditional protected mode. So all it does is it restricts you to areas of the file system which have a low integrity label set. And so we can open temp, and see, the bug effectively comes about because you cannot write to temp directly. So temp itself is, you need to be a high privileged process to write to it. But IE creates a low directory for you. And the low directory just so happens to be accessible by low integrity, probably unsurprisingly given its name. So while we can't write to temp, we can write to low, temp low, and we can then create our junction there, and we can do the exploit. So, okay. So this is, if I remember what it's called, so inject DLL, 1058, and CB. And so this is just a simple, there's various different ways you can exploit this, but in this case, all I'm doing is I'll write a batch file to the startup folder, your user's startup folder, so when Explorer starts, when they log back in, it'll potentially pop calc. So I run that, oops, what was it called? I'll obviously call it something different. Sorry about this. So 3604. Okay, shell startup. So we've now ended up with a batch file in there, and I'm sure if I actually logged off and logged back in, and this will probably not work now. It's I'm getting it's a bit risky. And hey, it didn't work. Yeah, Windows 8 is a bit weird when it comes to startup folders. It doesn't always. I've obviously done something horribly wrong. Oh no, there we go. We're just taking its time. Okay, so I think that's basically it, I think, for the first half.